Okay, to start off this video, I'm going to start a little differently. Rather than just starting with nitrogen, I'm going to draw an energy level diagram, but I'm going to include everything from hydrogen up to fluorine on it, and I want to show you something. And it makes a big difference it'll make a big difference in this video, okay? So, if we look at hydrogen, if we look at the 2s and the 2p, 2s, 2p, they are actually degenerate, okay? And they have a pretty high energy. Now, if we look at helium, they're no longer degenerate, but, whoops, I didn't do that right. This is supposed to be a little bit lower in energy, and then we have the 2s. And what you're going to notice here is as we go along, they're going to get lower in energy, and then the 2s and the 2p are going to get further apart. And I'm going to stop writing 2s and 2p, okay? Because I think you can figure that out on your own. And something is going to happen, and it's not at all obvious, whoops, why it happens, and I'm not even going to really talk about it. Actually, I take that back, I am going to talk about it. I'm not going to make you worry too much about it, but what is increasing as we go from hydrogen to helium to lithium to beryllium to boron is that the nuclear charge is getting larger and larger. And of course there's a 1s here, but we're not worried about the 1s. It just makes the drawing more complicated. As we go, the nuclear charge gets larger and it tugs on these guys more and more, and so they get lower in energy. They get closer to the nucleus, in other words. And that gap between the 2s and the 2p becomes larger and larger and larger until something really important happens at oxygen. Okay, and it's not going to be obvious, but this gap becomes large enough that we have no what we call sp mixing. Okay, I know you're not at all sure or have absolutely no idea what that means, but it will make a big difference when we do the orbital diagrams. Okay, so here there is no sp mixing. Well, the reason that is this energy difference is large enough so that the s and the p's don't interfere with each other energetically. Now, like I said, I know that doesn't make a lot of sense, but that is the explanation for what is coming, okay? So just remember that. For oxygen, fluorine, neon, there's no sp mixing, and that will make a difference when we do the orbital diagrams. So we did carbon last time, okay? I'm going to just go through the rest of these quickly because nothing really changes from now on. I'm sorry, nothing is changing. For nitrogen, it's exactly the same as carbon, except for we add a couple of electrons. Yeah, so 2s, 2p, 2p. Why do I keep drawing a D? 2p and 2s. And we get the sigma 2s, sigma star 2s. Pi 2p, sigma 2p, pi star 2p, and then sigma star 2p. Okay, and one thing maybe I haven't pointed out, I'm not sure. If we draw a line, connecting the 2p orbitals, notice that the bonding orbitals are always lower in energy than the native atomic orbitals, and the anti-bonding are always higher in energy. energy, okay? So add electrons here. 1, 2, 3, 4, and 5. And then over here as well. Oh, forgot to connect the dots. And I can hear my cat wants to go out. He'll just have to wait. Okay, so there we go. I just like to do that because it helps keep things a little bit more orderly. So we have 10 electrons. We start at the bottom, we go up. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, there we go. So answer the same questions we have been answering: paramagnetic, diamagnetic. This is, of course, diamagnetic. And looking at bonding or bond order, I find it much easier to just look at what's going on in terms of bonding versus anti-bonding. So these guys, they cancel each other out. Bonding and anti-bonding, they cancel each other out. But look up here. Now we have 3 bonding orbitals filled. Well, if we have 3 bonding orbitals filled, that's a bond order of 3. And of course, if you want to count it all up, it's 1, 2, 3, 4, 5, 6, 7, 8, minus 2 over 2, and that's 3. All right, that was nitrogen. Now oxygen. And here's where that sp mixing comes into play. O2. Oh, by the way, do the Lewis structure for nitrogen. What do you see? Triple bond. Okay, bond order 3. Not a coincidence. Oxygen, we have 2s, 2p. I'm sorry, that was 2s and 2s, and then we have 2p up here. Alright, somebody's screwing with me. I know one of you guys is out there messing with my computer, and I'm not smart enough to figure it out. That's alright. Okay, there's the 2p, and then this part stays the same. Sigma 2s, sigma star 2s. Now here's where the difference is. The pi 2p and the sigma 2p switch places. So now we have sigma 2p, pi 2p. Now up here it stays the same. Pi star 2p and sigma 2p. So the important difference is that from nitrogen to fluorine, these guys switch places. I'm sorry, from nitrogen to oxygen. Now from oxygen, fluorine, neon stays the same, okay? Now we're going to add our electrons. And we're just going to have one more for each atom than we had last time. All right. Play connect the dots. Okay, and I know this video is going to run a little bit long, but I just want to finish this out. Oops. So we don't have to come back and watch another video. So we have 1, 2, 3, 4, 5, 6 times 2, 12 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Paramagnetic, diamagnetic. Whoa, tricked you. Paramagnetic. So, in the video of them pouring the liquid oxygen through the magnet, these 2 electrons are explain why that happens. It doesn't matter if they're bonding or anti-bonding, they are unpaired. Okay? Bond order. Bond order. Let's look. Okay. These guys cancel each other out. These two cancel out one of these, doesn't matter which one. That leaves us with 2 bonding orbitals filled. Gives us a bond order of 2. You can do the math, you'll get the same answer. Oh, and O2, remember the Lewis structure, bond order of 2. All right. Fluorine. Diatomic fluorine. Yikes. Alright, let's run through this real quick. 2s, 2p, 2p, 2s. Now we have the sigma, 2s, sigma star, 2s. Remember, we have pi, 2p first. No, we don't. Who's the teacher here? We have, I'll get it, trust me, I'll get it. We have sigma 2p first, and then we have pi 2p next. Then we have the pi star 2p and sigma star 2p. Okay. Electrons. We have 14 to play with here. We start in at the bottom and we go from there. Okay, so let's fill them in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. Paramagnetic, diamagnetic, diamagnetic. Everything's paired. And bond order. And again, I just like to say these guys cancel each other out. These guys cancel those guys, so we're left with just what? 1 bonding orbital. It gives us a bond order of 1. Single bond. Fluorine, diatomic fluorine. There's the Lewis structure. Tying it all back together. Okay, now sometimes you might hear, well, what about F2 plus? What about F2 plus? Well, let's just do that real quick. I'm just going to modify this, okay? So if it's F2 plus, that means we've lost an electron. So does it matter where we lose that electron? And the atoms, it doesn't matter. We can just cross one of these guys out, okay? But we've got to take out one of these higher electrons. And now that completely changes our answers for paramagnetic versus diamagnetic. Okay? So let's just look at that real quick. Paramagnetic for F2 plus? Yes, it's paramagnetic. Why is it paramagnetic? Because we got rid of that electron and now we have an unpaired electron there. What about bond order? This is a little more complicated, okay? So let's just actually count everything up. 1, 2, 3, 4, 5, 6, 7, 8 bonding minus 1, 2, 3, 4, 5 anti-bonding. All divided by 2. That's 3 over 2. That is a 1.5 bond. So, did that strengthen the bonding in F2 or did it weaken it? It strengthened it, okay? This is a stronger bond. That's somewhere between a single and a double bond. Okay, now you guys can do diatomic neon on your own. I am out of time.